Okay, hi everyone, good morning.
Good morning.
The lecture is cancelled today. Uri is sick. Okay, I get it now, this message. Uri is sick.
So we don't have class.
Yes, you need to look recording with him about convergences and LLM. Okay.
Yeah, convergence and
LLM, etc. limit theorem or low of large numbers. LLM. Okay. Okay. So let's start. Today we're at recitation number 10. Here you have quiz about generating functions. Okay, you have quiz, and this is our slides for today. Let's move it here. Okay, let me make it a big. Okay, let's start. Okay, probably it's better. Okay, today we continue to talk about inequalities. Okay, we'll talk about Markov inequality, Chebyshev inequality, and Chernoff inequality, and Hoeffding inequality. There are many of them. Okay, they're very useful both in statistics, in probability, and in machine learning, in data science. So let's start from review. Here you can see two forms. It's the same thing, yes, of the Markov inequalities. We can use Markov inequality if x non-negative. It's important. If x is a non-negative random variable, then for every lambda greater than 0, probability that x greater equal lambda less equal expected value of x divided by lambda. This is the first form, and this is the second form. Okay? I like more second form, but it's the same thing. The second form says the probability that x greater than a times its expectation less equal 1 divided by a. Okay, but this is the same thing. Chebyshev inequality. In general, can be stronger, but here we need to know two things: expectation and standard deviation. Okay, and what does it say? It says that probability that random variable, absolute value of difference between random variable x and its expected value will greater equal k less equal variance of x divided by k squared. And again, we can use this form. Yes, probability that absolute value of x minus mu greater equal a times standard deviation less equal 1 divided by a squared. Both these two statements is equal. Okay. Chernoff bound is a stronger bound, but it's harder to use. Okay. Probability with random variable x greater equal a less equal expected value of e power lambda x divided by e power lambda x. Pay attention, here we have parameter lambda. It can be any number greater than 0. So here we have inequality in the form of function of some parameter lambda. You can choose any lambda greater than 0. But we want our inequality to be tight, yes, to be precise. So we choose lambda that minimize this expression. And how we can find minimum function? How we can find minimum of some function? By the derivative, yes. So here, in general, we need to solve optimization problem, yes. We need to find lambda that minimize this expression. Yes. It's any number. It's correct for any lambda. But if we want to build strong inequality, we will choose lambda that minimize this expression. So lambda is any parameter, and we want to choose lambda that minimize this the right size of this expression.
I feel like lambda is like a canonical parameter.
Yes, it's a parameter, yes. It's correct for any lambda.
Yeah.
Lambda equals 100, 1 million, 1, 0.1 for any lambda with inequality, correct?
Kind of like optimize something, we call it a lambda.
Yes.
But why it needs to be bigger than zero? When we do NGF, it will has to be bigger than zero.
It's a statement. Okay. When you solve optimization problem, you find lambda with greater than zero that minimizes expression.
But what happens if looking for the minimum value and I do the derivative and find lambda is smaller?
Okay, then you choose lambda. You need to find lambda that minimize this expression, yes? Constraint lambda greater than zero. This is a minimization problem with constraint. So in this case, when lambda, if you will find when this expression has minimum with lambda greater than zero, smaller than zero, you need to continue investigation. Probably lambda equals zero, probably something else. You need to continue. Yes, it's a optimization problem with constraint.
Okay.
Well, in many situations, lambda will be greater than zero. Yes, in real examples, yes. Okay. Let's return to our previous question about miner trapped in a mine. Do you remember this question?
Yeah.
Okay. It's trapped in a mine containing three doors. Door 1 leads to safety after 3 hours of traveling. Door 2 returns him to the same room after 5 hours of traveling. And door number 3 returns him to the same room after 7 hours of traveling. Okay. Now, the question is, where is it? We want to use Chebyshev inequality to bound probability that x great equal 100. Okay. We want to use Chebyshev inequality to bound this probability. Pay attention, in the previous class, in the previous lesson, we found the probability that x great equal 100 less equal 0.15. Okay, it's something, but it's not very good estimator count. So now we want to use Chebyshev inequality. But to use Chebyshev inequality, where is it? We need to know standard deviation variance. Yes. Okay, so let us find us. Okay, variance of x equals expected value of x square minus square of expectation. Expected value of x we found in the previous lesson. So now our goal is to find expected value of x squared. How we can do it? We have a couple of possibilities. If you remember, in previous lesson, we found generating function of x, probability generating function of x. In general, we can use probability generating function of x to find its variance. We have formula, okay? But now here we want to find expected value of x squared using the formula of conditional expectation. If take expected value of x squared by the formula of conditional expectation, we have three cases, yes? With probability 1 over 3, x equals 3. So here we have square of 3 power 2. With probability 1 over 3, we have here 5 plus x, y. He chooses the second door, he goes 5 hours and return to the same room. The process restart himself. Yes. So here we have 5 plus x squared. And if he chooses this third door, he goes 7 hours and the process restarts itself again. So here we have 7 plus x squared. Now we need to solve this equation. Okay, we open brackets and we solve. Yes.
Why do you look for each raise in 1/3?
Because this, okay, good question. The miner chooses a door uniformly at random probability 1 divided by 3 for each dog. It's given in the question, okay? With the same probability, he chooses any of these 3 dogs. So it's given. Good question. Okay. So we have here linear equation for x squared. We open the brackets, we solve it, and we get expression for expected value of x squared. Okay, and now we know the variance of x. It equals expected value of x squared minus square of expected value, 218. Or you can use generating functions. But in this case, you need to find second derivative of generating function. Okay, so
What did we do a root?
can you repeat?
How was it a show?
Because we want to know standard deviation. Look in the, let's look at Chebyshev inequality. To use Chebyshev inequality, we need to know standard deviation. Okay, so we found variance and square root is a standard deviation.
Yes, variance is standard deviation is variance squared.
Yes.
That's why we.
And now we're almost ready to use Chebyshev inequality, but not yet. Our goal is to estimate, to find bound for probability that x greater equal 100. But it's not on the form of the Chebyshev inequality. Yes, the form of the Chebyshev inequality is the probability that absolute value of x minus its expectation greater equal something. It's not same form. So we need to do something. Okay. We put here absolute value. We subtract expected value from x from both sides, 50, and we put here absolute value. Now we have here 2 intervals, x greater than 100 and x less equal sum. Probability of union of A and B always greater equal probability of A. So we have this inequality. Make sense?
But I got something else. I could have write x minus 30.
Yes, but you want to use Chebyshev inequality, and Chebyshev inequality, where is it? Before you need this form, probability that absolute value of x minus its expectation. At expectation equals 50. You want to use this form, okay? Because it's theorem. Okay. Okay. And now for Chebyshev inequality, this probability less equal variance of x divided by 85 square, it equals 0.03. It's smaller than bound that we got using Markov inequality. It's not always correct. Sometimes Markov is better probably, but in general, Chebyshev inequality is better than Markov because we use more information. We use here information about expected value and about standard deviation. So in general, it's better, but not always. Okay, it's clear? Okay. Now, okay, take home message, as you see, Chebyshev inequality usually provides much tighter bound than Markov because it uses more. Okay, that's what I said. Okay, before we solve question 1.5, let's solve question 0.2, problem 2. Okay. It's also interesting question. Let's look on it. Okay. We want to prove that it's impossible to improve Markov inequality. It's impossible to improve it. Okay, and this is the Markov inequality. Okay, how we can prove that Markov inequality is equal? We can provide an example of some random variable such that for this random variable, this equality turns to equality. So we can conclude that it's impossible to improve Markov inequality because for some random variables, it's equality. So this is the goal of exercise number 2, problem 2. We want to construct random variable x such that Markov inequality becomes an equality. So you need to invent such random variable. There are infinitely many solutions. Okay. If you have enough time, yes, I can say you sit in this class 1, 2, 3 hours and invent such examples. It's not hard, it's not easy. You need, usually people need time to find the solution, So I will demonstrate you one of examples. Okay. How I found this example, how people can found this example? By trying. Okay, so let us construct simple binary random variable, llama binary, because it's simple. Yes, if we want to build example of random variable, such as this inequality turns to equality, we want simple example, and one of the simplest things is a binary random, Bernoulli random variable. Okay, if it's binary, we can choose something. For example, 0 and lambda. The probability, it's not Bernoulli, it's binary. 0 and lambda, with probability p and 1 minus. This is example. And my statement is, for this random variable, Markov inequality is equality. So we can't improve in general Markov inequality. Because it's equality, it's impossible to improve equality. Again, if you think how I found this example, I'm trying. Yes, it's Yes, we need to try. So it's a final solution. Yes, it's not all the way to find this solution. But now we need to demonstrate that for this random variable, Markov inequality is equality. Okay, let's do it. Let's do it. Okay. Let's do it together. So Markov inequality says probability that x great equal lambda less equals expected value of x divided by lambda. Yes? Okay. For this random variable, what is the probability that x great equal lambda? For this random variable. P, it's a probability that x equals lambda, it's a p. This is exact solution. You agree? But now let us use Markov inequality to bound this probability. Okay, let us use Markov inequality. Okay, can we use Markov inequality? Yes, because it's not negative. Okay, so probability that x great equal lambda by Markov inequality less equal expected value of x. Can you find expected value of x? Lambda. P lambda, yes, P lambda. P lambda divided by lambda equals P. You see, this is the exact answer, and this is Markov estimate bound. It's the same thing. So from here we can conclude it's impossible to improve Markov inequality. For some random variables, it's equality. That's all. The solution is clear?
Yes, so just in terms of the expectation of x being p times lambda. Is that a
You want here put expected value of x?
No, just we have an expectation of x, right? We know that was p lambda. Like why?
Yes, p times lambda plus 0 times 1 minus h. By definition of expectation.
Yeah, okay.
It's lambda. Yes.
But where's the 1 minus?
Lambda times p plus 0 times 1 minus
One, yeah, 0.
It's lambda p.
So this is Bernoulli we can find easily, but if it's Poisson or geometry, it's we can also.
Yes, but it's in general question. Here you can build any random value. Yes. But in this question you don't need to. You can choose any x you want. The simplest one is Bernoulli, not Bernoulli. It's finally random variable. You don't need for this question choose Poisson. But in general, yes, in general, it can be very hard to find example in general. But for this question, it's not very hard. Okay, here you see, you can find the solution. Just a moment. Okay, here the solution. Okay, take home message. You can read it at home if you want. Markov inequality is a type. It's an impossible improvement. Okay. And now let's return to question 1.5. Here we want to prove a Chebyshev inequality is type. It can be improved in general. It's same. Synonymous. It can be improved. Okay. And again, if you want to prove which Chebyshev inequality is type, it's enough to provide an example for some random variable such that inequality goes to equality. That's all. Okay. And again, here example, if you think how I can to choose this example, okay, we need to think. But in general, that's some intuition how we can construct this example. First of all, for the simplicity, we can choose some random variable with zero expectation. For simplicity, it's a good idea. Yes, because we can remove this term. Okay, so we want to build some kind of symmetric random variable. 0, k minus k. Okay. And this is a random variable. It's symmetric. It equals minus k or k with probability 1 divided by 2k squared. And it equals 0 with complement of these two things, 1 minus 1 divided by k squared. Okay. And now we need to check, it's enough to check that for this random variable, the Chebyshev inequality is equality. That's all. So this final thing we need to check. Okay. So let us check again. Everyone sees, if everyone sees that expected value of x is 0, it's symmetrical. It's symmetrical. Yes, it's symmetrical. Okay. Let us find the expected value of x. Variance of x. It equals expected value of x squared minus square of expected value. It's 0. Minus -0 squared. Make sense? Why no?
Why minus 0?
Because variance of x equals expected value of x square minus square of expected value, and expected value equals 0. It's symmetrical random variables. It's dynamically symmetric. The expected value of x equals 0 because it's symmetric random variable. Yes, this random variable is symmetric. You can find its expected value by definition. Minus k times this probability plus 0 times this probability times k plus k times this probability, it equals 0.
But we also specifically need the variance to not be 0, right?
Again?
We also need the variance, we need the expectation to be 0. But
We choose examples.
But the variance can't be 0.
Yes, it can be 0 only for constant random variable. Constant. If x equals 5 with probability 1, the variance is 0.
Right.
Okay. So variance of x equals expected value of x squared. Okay, we need to find expected value of x squared. How we can find expected value of x squared? Please help me. By definition, yes. Minus k squared times 1 divided by 2k squared. 0 square plus times this probability k squared times this probability. Yeah. Okay, so expected value of x squared equals k squared divided by 2k squared plus 0 plus k squared divided by 2k squared, and we get 1. Yes. So variance of x equals 1. Yes.
That's the reason you chose the probability to become 1 over 2k squared. So the variance of
Okay.
1.
If you want to understand how I find it, first of all, before I know the answer, here are parameters a, 1 minus 2a. And I solve equation until the end, and I saw that a must be equal this value. So this is final solution. Okay, if you
have to be this fellow y, so the variance become 1. That's the reason.
Oh, yes, it's simple. Yes, the simple thing is to choose another variable with expectation 0. And the second idea, we want to put same mass here. Yes, but variance equals 1, for example. Yes, I also can choose 5. It doesn't matter, but something. But 1 is the simplest thing for our calculation. For the variance of x equals 1. Let us remove unnecessary things. So what we know, what we proved, we know what expected value. Just a moment. Okay, expected value of x equals 0, and variance of x equals standard deviation of x equals 1. Yes? Okay, let us use Chebyshev inequality now. Okay, what is the probability that x great equal absolute value of x great equal k? Use definition, not Chebyshev inequality. Use definition of x. Look on x. What is definition of the absolute value of x great equals k? It can be or here or here. Yes? It equals 1 divided k squared. That's all. Probability that x, absolute value of x great equal k equals 1 divided by 2 times k squared plus 1 divided by 2 k squared. It equals 1 divided k squared. This is the exact answer. Now let's use Chebyshev inequality. Yes, probability that absolute value of x great equals k, let equals 1 divided k squared. Yes?
Yeah.
So, for this random variable, Chebyshev inequality turns to equality. It's time. It's sharp. You can't improve it in general.
I have a question. No?
Mhm.
How can you describe a situation like on the left hand side expressions, the probability that absolute x is great? It doesn't matter if it's absolute x or just x. X greater than equal to something. I'm asking because we are using here discrete random variable.
Yes.
So discrete random variable, it's like just p equals x equals 2 something. What is x greater than something?
No, in general, okay. In general, x great equals k. What does it mean? X equals k,
Okay,
or
plus 1.
x equals k plus 1 until infinity.
Okay.
But for this random variable, x great equal k is simple probability x equals k. Because it can get only k minus k of 0 values. But in general, you need to find this sum. Yes. K plus 1, k plus 2 until infinity.
So the k plus 1, k plus 2, and so on is 0?
For this random variable. Yes,
Yeah.
yes. This is idea.
Because we have four.
Yes, and because they're disjoint and oh yes.
So in terms of we said the variance is 1,
Yes.
right? So
Standard deviation is 1. Yes.
yeah, but how did we didn't if we do x squared, isn't like how does that get like I guess the negative signs, I didn't see them cancel. shouldn't they like, shouldn't it be like, how did we do x squared? How did we get x squared? You know?
Expected value of x squared?
Yeah, because I mean, to get the expected value of x squared, we need to find x squared, right?
Yes.
What exactly?
It's enough to find. No, we don't need to. It's enough. Yes. Expected value. Just a moment. Where is it here? Expected value of x squared. By definition, for discrete random variable,
Yeah.
it equals sum for I from minus infinity to infinity. Yes. Minus y mean infinity to infinity. Now you need to apply this function on I square, because we find probability of x square, times probability x equals I. And now, here we have only three cases, yes? Minus k, 0, and k.
Okay.
Minus k square is a k.
Yeah.
So here we have k times this probability. Product
Yeah.
plus 0 square is
Yeah.
0
Yeah.
times this probability. Okay, 0.
Yeah.
Plus k square
Yeah.
product with these numbers.
Yes.
And we get the answer.
Yes, so that's like what k squared over 2k.
K over, yes, it's 1 divided by k, 2k.
Yeah.
Oh, it's 1 over 2.
It's 1 over, yeah.
It's 1 half plus 0 plus 1 half. It's 1.
Just okay, because you're filling in, because k is like what?
K is some number, yes. Pay attention, yes, k is some number. You can choose k.
Okay, so yeah, so the basic idea is a k cancel. There's just k is
K squared cancelled with below with k squared below.
so it's just 1 over 2 k squared.
Yes.
So then how do we get from 1 over 2 k squared to, because to me
Expected value of x squared. We have solution below. Equals k squared for this k times 1 divided by 2k squared. It's 1 half plus 0 times 1 minus 1 divided by k squared. It's a 0, yes? 0 square of 0. Plus this guy, k squared times 1 divided by 2k squared.
but shouldn't there be more than k squared on the bottom? Because didn't we
This guy, it's equals 1 half.
Yeah, I just when we squared it, isn't it?
Minus k square.
Yeah, no, yeah, exactly. But the probability 1 over 2k squared.
We won't need, no, pay attention to this formula. We expected value of x square, we only put square on the I.
Yeah.
We don't put square on probabilities. No, only on the values of I. Here we won't use square.
So when we say probably that x equals I, that's probably that x equals k, or what? Or probably
In this case, it's y. But in general, it's I. But for this case, it's k. It's minus k times square times this probability, plus 0 square times this probability, plus k squared times this probability. That's all.
okay, but so it's sort of. I just isn't that exactly the same as the expectation of x?
Oh, it's expectation of x squared. Pay attention.
I'm just not really seeing where the square is, you know?
Okay, let me probably explain it here. Just a moment. Okay. First of all, let's see. Okay, let me explain it again. Okay, look here, yes. Variance of x equals expected value of x squared minus square of expectation is 0, minus 0. Expected value of x squared equals minus k squared times probability that x equals minus k plus 0 squared times probability x equals 0 plus k squared times probability x equals k. And all this
stuff squaring the k's and not the probabilities.
Yes, only k, only, yes, probability with what touch, yes, yes. Okay, we do it. Okay, let's do the last question. Before that, I want to remind you moment generating function. Do you remember? Do you read about this? Moment generating, okay. We have many generating functions. Probability generating function, moment generating function, characteristic generating function, quantile generating function. Okay. Why we need all of them? In general, characteristic generating function enough. It's the strongest generating function in some case, in some sense. But it's the hardest to use because it's complex, function of complex random variable. So for partial case, for special cases, we can define simple generating function. For example, in previous lesson, we talked about probability generating function. It's a simple generating function, but we can define it only for non-negative integer random variable or some special case. Moment generating function we can define for non-negative random variables, for example. It's more powerful. And how defined? It's defined in this way. Its expectation, it's a function of x, expectation of e power t. And t is a parameter. So you can ask me, what is this parameter? What we want to use this random variable, this generating function, because it has many nice properties. For example, it's an uniquely deterministic distribution of random variable. It allows us to generate moments. Using this guy, we can find the derivative and calculate moments of this random variable. So it's useful to find moments. It's also useful to find distribution of sum of random variables. If x and y is independent random variables, the generating function, moment generating function of their sums equals to the product of moment generating function. It's a very powerful result. It's very useful theorem. You can think about generating function as a canon. It's very powerful weapon. As I said in previous lesson, the course in mathematics faculty about generating functions. You can study whole course about this one. Okay.
But
Yes.
We can use on the negative random.
On positive, non negative.
Only in positive.
Non negative. Yes.
No,
Yes.
PGF, I thought.
No, PGF integer.
PGF,
Integer and non negative.
yeah.
And MJF, you remove the integer
Oh, so it's you.
And the characteristic.
for any. But it's hard to use because it's
including negative.
yes. But it's hard to use because it's a function of complex random variable. Yes.
Yeah.
So this is last question for now. The additional question, I advise to read them. Yes. Okay. The last question for now, question number 3. We have x, Poisson random variable, and we want to prove to find upper bound to probability that x greater equal to n. For Poisson random variable. Let me remind you about Poisson random variable. X, just a moment, x is a Poisson random variable. The support of x is the integer numbers from 0 to infinity. And probability that x equals k equals e minus lambda times lambda power k divided by k factorial. Expected value of x equals variance of x equals lambda. Poisson processes is a very important family of stochastic processes. It's very, very useful. In the nature, many processes behave in approximation as Poisson. So it's very important random variable. And now our goal is to find upper bound for probability that Poisson random variable great equals n. And we will use Chernoff bound, Chernoff inequality. It's a calculus question. We need to define some function and find its minimum. Okay, let's see. Okay, we want to find upper bound for this probability. By Chernoff inequality, it less equal. You remember okay, let me demonstrate to you. Here we use lambda, yes? Where is it? Yes, you use lambda. In solution, we use theta instead of lambda. Okay, it's the same. This is Chernoff bound. It holds for every lambda, and we choose lambda that minimizes this expression. Okay, let's do it. In our solution, instead of lambda, we use theta. Does not matter. Where is it? Question number 3. Okay, yes, it's here. We want to bound from above probability that random variable x greater equal n. By Chernoff inequality, it's less equal expected value of e theta x divided by e theta n for every theta greater than 0. No. And now we will choose theta greater than 0 that minimize this expression. That's all. You can choose, put here any theta, 0, 1, 10, million, 1 divided by n, but we want to choose theta that minimize this expression. Okay, but first of all, we need to simplify this expression. Expected value of e theta x. How we find this guy? Expected value of e theta x. How you will find this guy, this fellow, this expression? You can use definition, yes? It equals sum. Why sum? Because x is discrete random variable. I goes from 0 to infinity. E power theta I probability that x equals I. This is definition, yes, for expectation of function of random variable. Make sense? Okay, you can do it. You can do it. You can solve this question. It's not very hard. It's 2 lines, and you can solve. But you don't need. Why? This fellow, this guy, is a moment-generating function. It's definition of moment-generating function for Poisson. So you go to the book, to the table, and you look in the book the expression for the moment-generating function for Poisson random variable. And here we are. This is the final answer. But in general, my advice to you, solve this question. Yes, it's 2 lines. It's not so complicated. Okay. So expected value of theta x is a moment-generating function for Poisson random variable, and this is final expression. So here we have e power lambda e theta minus. My advice, find it in MJ for these random variables because it's not very hard. It's instructive to do. Show next step.
But in the exam, we need to remember this whole.
It depends. Okay, it's question for theory. Okay, it's okay. Sometimes he can give you hints, sometimes not, but it's good question for theory. It depends. Okay.
Need to remember.
I don't know. Do you okay? But again, you can find this expression in general. Probably it will be given. It depends on theory. You can ask it. Okay, I don't know. I don't. Okay. So by Chernoff inequality, probability that x greater equal n less equals this term for any theta greater than 0, for any theta. And now our goal is to find theta that minimizes this expression. Okay, how we do it? We find derivative by theta equals 0, find solution, check the second derivative. We don't do it now, but this is idea. So find first derivative. Okay. Substitute back. Okay, here in general we also need to find second derivative to ensure that it's a minimum. Okay, this is final solution. Let's see. Not here, it's here. Probability with random variable n greater equal n equals all random variables, let's equal this expression. It's very tight bound, it's very good bound, and this is a and take home message. Choose theta that minimize the expression. Okay.
And just quickly, so how did we actually do the infinite income? Or the minimizing it?
You need to find derivative. You need to set right expression derivative equals to 0. You need to solve it for theta. Where is it? Here the solution. And in general, you need to check second derivative. Because probably it's not minimum, probably it's maximum. Yes, you need to check. I need to add this. Okay. You need to check second derivative. Probably it's maximum, not minimum. That's all. Okay, read also problem 4, it's good problem, and all of them good problems, okay? Yes. Okay, so we stop here. Let me remind you that Ori is sick, but he asked to look his lecture about convergences and law of large numbers. It's not easy material. I think it's the hardest material, but it's very, very important for the next course, for statistics course. But in general, it's very important topic, convergences of circles of random variables. So try your best to understand, because it's very important material. Okay, that's all for
But I
today.
think we don't have the notes. LLM, law of large number, we don't have.
I think let's see, let's check. I don't know. Let's check.